The next presentation module is devoted to another design for trust approach called split manufacturing. In split manufacturing, the threat model is different compared to logic locking or logic encryption, for instance. Here, the assumption is that the foundry, the fabrication facility, is untrusted, while the end users are trusted. So what does it mean to trust the end users? Well, if we know that the chips will go into devices that will go to the end users whom we trust, this could be maybe in the form of a military application where the devices will be distributed to the trusted parties, then we're talking about trusted users. So for such a scenario, for such a threat model, split manufacturing is the appropriate technique to employ. So here we're trying to protect ourselves from the untrusted fab. So as we know, the chip, the integrated circuit, consists of metal layers. The bottommost metal layers have the information regarding the transistors. These metal layers are referred to as front end of line metal layers, FUL metal layers. These are the first 4 metal layers from the bottom. For these metal layers, the pitch is typically very small because the transistors are very small in size, and this is precisely why we need a high-end foundry to fabricate our chips. That's why more and more design companies are going fabless to be able to manage the manufacturing of these FUL metal layers. And then we have the top metal layers that we refer to as back end of line metal layers, or BOL metal layers. These are typically metal 5 and above, where the pitch is large. And this part of the chip is much easier to manufacture because, as I said, the pitch is large. But traditionally, when you want to manufacture a chip, you send the entire layout to one fabrication facility, and there both the FOL layers and the BOL layers are all fabricated together. So you need a high-end foundry simply because you need the FOL layers to be manufactured in a high-end foundry. The question is, now that we understand that there are trust issues and we cannot fully trust these foundries, can this asymmetry be leveraged for security? The fact that the FOL layers are difficult to manufacture, but BOL layers are easier to manufacture. Can this be leveraged for security? And that's what IARPA has been promoting. IARPA came up with the idea of split manufacturing, where instead of a single fab to manufacture the entire chip, can we use multiple fabs to manufacture different parts of the chip? Namely, we use one fab to manufacture FOL layers and another fab for the BOL layers. So this way, no single fab has the entire information about the layout, and we're hiding some information from each fab. So for such an idea, the flow needs to be modified a little bit. Everything up until the generation of the layout can remain the same because we're producing the same layout, but once the layout is ready to be sent to fabrication, that's where the split needs to take place, and the split happens based on the metal layers. So the layout is split based on the BOL layers and the FOL layers, and the two split pieces of the layout are sent to 2 different fabs. The BOL layers are sent to the BOL foundry, and the FOL metal layers are sent to the FOL foundry. So there are 2 different strategies that can be followed in split manufacturing. You could use exactly 2 foundries to produce 2 pieces of the chip, and then you can take them and align them and sandwich them in a trusted place. That's one way to do split manufacturing. The other approach can be to manufacture the FOL layers in an FOL fab, and then take those wafers and then grow the BOL layers on top of the FOL layers in a trusted foundry. So these are 2 different ways to accomplish split manufacturing. Now, what does split manufacturing get you in terms of security benefits? At least, what does it intend to get us in terms of security benefits? Well, the untrusted fab, which we can normally assume to be the FUL fab, does not have the entire information about the layout. they don't have access to the BOL layers. So any information about your layout that is defined at the BOL metal layers, the top metal layers, this information is not available to the untrusted parties in the FOL fab. So this way, because they don't know the entire layout, they can't fully understand the design implementation details, they can't fully understand the functionality of the chip. So the hope is, because of this missing piece of information, they will not be able to insert meaningful Trojans, they will not be able to find safe places to insert Trojans, they will not be able to definitely overproduce the chips because they're missing the BOL, all the connections defined at the BOL layers, and even if they reverse engineer whatever is available to them, they can only get all the information that is defined at the FOL layers only. So these are the security benefits that split manufacturing intends to deliver. But there are, of course, challenges, and these are mostly logistical challenges. Transporting wafers from the FEOL foundry to the BOL foundry without damaging them. Alignment of the FEOL and BOL wafers and layers. All sorts of problems regarding signal integrity, timing, reliability. So these are the challenges associated with split manufacturing, but yet IARPA announces that they've made significant progress with split manufacturing, and they've successfully implemented split manufacturing for 130 nanometer technology. So is split manufacturing secure? In other words, can this defense be attacked? Or what does it mean to attack split manufacturing? Well, obviously, the idea is, if we assume that the FEOL foundry is untrusted, and that's precisely why we're doing split manufacturing in the first place, they're trying to recover the information that is missing for them, which means they're trying to understand the missing connections defined at the BOL layers, because that's what's missing for them. If they can reconstruct that information, then they have the entire layout information available to them. So that's the threat model. And the objective is obviously to determine the missing connections, the missing wires defined at the BOL layer. Now we have defined a very simple attack a few years back that we refer to as proximity attack, and the idea there is basically leveraging the way the heuristics work, the physical design tool heuristics work. What we do in a proximity attack, or what the attacker can do in a proximity attack in the FEOL fab, is they can simply make the connections between the closest pins. This basically relies on the assumption or the heuristics that the physical design tools place components that are to be connected at the BOL layer as close to each other as possible. So if you can make the connections, missing connections between closest pins, that is highly likely to be the correct connections. So it's a very simple attack. You just connect the closest pins together, and you hope that those are the right connections to make. So that's how proximity attack works. And in the process, there are certain additional pieces of information that can help the attacker. For instance, you would know that input ports can only be connected to input pins, and same goes for outputs, so you don't make obviously wrong connections that way. You also know that combination loops should not be there in the design, so when you make the missing connections, you pay extra attention to make sure that you don't form any combinational loops, because that'll be obviously wrong. So there are certain things that you can use to prune the search space and limit yourself to making the correct connections. And this way, with proximity attack, you can hope to get most of the missing connections correctly. And we've shown in the past that proximity attack can be quite powerful. Of course, it has its own limitations, but you can at least get most of the connections correctly. And you know, the community has been working on split manufacturing ever since we came up with the proximity attack about 4 years ago. People developed defenses. Another group from UT Dallas, also along with Texas A&M, they developed a more enhanced version of the proximity attack as well, and also the research community responded by developing more secure split manufacturing solutions. So in this module, I talked about split manufacturing. Split manufacturing is the right solution for business models where you trust the end users, the users who will use the devices that your chips will go into, but you do not trust the fabrication facility. Split manufacturing basically hides some of the layout information from the untrusted fab, and this delivers certain security benefits. Thank you very much for listening.